Well, hello there. Here we continue with the number and algebra unit. And everything here should be review, and so I hope to go through this fairly quickly. If you look right here, I'm summarizing a bunch of exponent laws, and while we are eventually going to look at logarithms, right now all I'm looking at are exponents. Everything you see here should be review, like I mentioned before, but the key is don't expect these to be on an IB examination booklet. None of these would be on an IB examination booklet. So instead of thinking about these as formulas, we want to internalize the sort of concepts here. That's it. Let's look at these two here, and I want to simplify these expressions. I want my answers to have only positive indices, or positive exponents in this case only. So if we look right here, I have 4a squared b cubed times c times 8a to the power 5 b to the negative 2 times c. And should be fairly quick. I essentially have a whole bunch of multiplication here, and I can multiply factors in any order. So I'm going to go 4 times 8 first, which is 32. Then I'm going to multiply my powers of a. I have a squared times a to the power 5, which when you multiply powers at the same base, you can just add your exponent. Because I have 2 a's times 5 more a's, that means I have 7 a's all being multiplied to each other. And then for b's, I have b to the power of 3 times b to the power of negative 2. And even without even thinking about what a power of negative 2 means, my exponent law is when I'm multiplying powers at the same base, I can just add my exponents. So this is going to be the same as b to the power of 3 take away 2. 3 take away 2 is 1. So does b to the power of 1, or does b. And then for c, I have just c times c, which is c squared. And while I'm done, I do want to make a comment about why b to the power of 3 times b to the negative 2 is just b. One way of thinking about a negative exponent is this means you're repeatedly dividing by b, which complements quite nicely positive exponents, which means you're repeatedly multiplying by b. So if you look at just the b cubed times b to the negative 2, I could think of this as being the same as b times b times b. That's the b cubed. But when I multiply by b to the negative 2, a negative power really means we're repeatedly dividing. So all this is being divided by b twice. And hopefully it sounds familiar that when you have negative exponents, we can tend to write them as in a denominator of a fraction. And if I look at this, I'm multiplying by b 3 times, dividing by b twice. These all cancel out. It's just one little lonely b left. And so while I don't need to show that every time, we do want to understand why a negative exponent, is the way it is, or it's kind of summarized right here. If you ever see anything to the power of a negative exponent, it's the same as dividing by that a number of times. All right, right here, just same idea, just getting a bit messier. And so I would first clean up my numerator here. And there's a few steps. Order of operations, I really should look at all of this first. This is 3xy to the power 4 all squared. And so please recall, when you have a series of factors all being raised to a power, you can think of each of those individual factors to that power. And so I can think of this as being, I'll leave the 2x squared z, whatever you want to call it, alone. And then inside here I have 3 squared, or just 9, times x squared times y. And then I have y to the power 4 to another power. Anytime you have a power raised to another power, you can just multiply those together. And so the same as y to the power of 8 all over my denominator. All right, and now I'm going to clean up my numerator more, although there's always choices, but now I'm going to do what I did before. 2 times 3 times 3, or 2 times 9, which is 18. I have x squared times x squared is x to the power 4. I have a lonely z, which I'll get to in a bit. I like to be boring and go in alphabetical order, so I have y to the power of 8, and then my little lonely z. And finally, I'm now going to focus on my denominator, all this divided by negative 4xy z cubed. And so I have 18 over negative 4. 18 over 4 is not a whole number, but it does reduce to 9 over 2. And the negative I can write in the numerator, or I'll just make my whole rational expression here negative. And then I have x to the power 4 divided by x, same as x to the power 4 divided by x to the power of 1. Either way, it's x cubed left in my numerator. I have y to the power of 8 divided by a single y down here. That means I have only 7 y's left in my numerator. And then I have a single z in my numerator divided by 3 z's in my denominator. I could use my exponent laws, and I could think of it as 1 take away 3 and think of this as z to the negative 2. But I do ask up here that I should only have positive exponents. So instead of doing that, and what I prefer to do is just think about what z to the power of 1 divided by z to the power of 3 means. And it means I have 1 z in my numerator. I have 3 of them down here. Well, I can just cancel one of these out each. And so I can pretty quickly realize I just have 2 z's being multiplied to each other in the denominator. So z squared in the denominator. And there's my simplified answer as requested. All right, same idea here, just getting more annoying. But same idea, we want our answer simplified with only positive exponents. And so while it's not wrong to take this power of negative 3 and just write everything to it, that gives me a headache. And so what I'd rather do is clean up what I have inside here. And so let's simplify the base of my exponential expression as much as possible. So for example, 18 over 6, that's just 3 whole. That's quite nice. I have x to the power of 3 divided by x to the power of 11. That I could use negative exponents, but I'm going to stick with positives right now. And so that means I have 3 x's in the numerator. I have 11 x's in the denominator, which means a bunch of them, 3 will cancel out from the numerator with just 3 of these. And so in the end, there are no x's left in my numerator and 8 x's left in my denominator. Or you could use exponent laws or whatnot. Over here, I have y to the power of 5 divided by y to the power of negative 1. Now let me focus on this divide by y to the power of negative 1. Dividing by a power of y to the negative 1 is the same as multiplying by y to the positive 1. And so if we think about it like this, I'm going to just kind of erase this for a second, because it's equivalent. Instead of having y to the negative 1 in the denominator, it's equivalent to y to the power of 1 in the numerator. And then I just have y to the 5 times y to the 1, which is y to the 6. Now that said, let me, just go back to how it was. Other options, there's lots of options always in the end. The more we can get the positive exponents, the less chance we have of making a mistake. And then I have my just z here, so I'll keep my z right here. Now, at this point, all of this has been cleaned up. It's still to the power of negative 3. And again, it's not wrong, and it's not as bad as before to write everything to the power of negative 3. But there's a lot of mistakes, especially that can be made when you have 3 to the negative 3. We can think this equals negative 27 or something like that, and it's not. So instead of doing that, just what I think is quite helpful, and we never want to forget, is that if you have anything raised to a negative power, especially a rational expression, I can always think of it as a positive power, change that negative 3 to 3, as long as I find the reciprocal. So instead of everything inside, instead of having 3y to the 6 times z and so on in my numerator, I can think of that in my denominator. And instead of x to the power of 8 in my denominator, I can think of it in my numerator if I change the sign from negative 3 to positive 3. Same idea that if I have 2 to the negative 3, that's the same as 1/2 to the positive 3. And that sort of idea of going from here to here and here to here is really, really important, that how we can manipulate expressions by changing the signs of the exponents if we want. Instead of always doing this almost mindless use of exponent laws. At this point, now I'm going to raise everything to the power of 3. And for the most part, I'm just having a power to another power. That looked really messy. Let's try that. And so first I have, and this will finish off my answer, I have x to the power of 24. Because when you have a power raised to a power, you multiply them. Then right here, I have 3 to the power of 3, which is 27. So I have 27 in my denominator. I have y to the power of 6 to the power of 3, which is going to be y to the 18. And then I have just z to the power of 3. So in the end, I have this fairly messy expression, but everything's simplified. There's no negatives left. And keep in mind, there's almost countless ways you can go from here to here. I would generally just try to avoid negative exponents as much as possible and just try to avoid trying to do too much at once. Lastly, I have an expression here with exponents that have variables in them. And again, I want to simplify this as much as possible. This time, I want my answer to have no rational expressions, no fractions. So writing your answer without any rational expressions. So unlike before, I perhaps want to have negative exponents, because when you use negative exponents, you never actually have to deal with fractions. And so first, what I have here is I got a base of 2 and I have bases of 3. But before I get to that, I have 3 to the power of b minus 1, and it's all squared. And so what do we do here? Well, I have a power raised to another power. And as we've seen many times already, when you have a power raised to another power, you can just multiply them together. And so this expression I can write as 2 to the power of a times 3 to the power of 2b minus 2, b minus 1 times 2. And then I have my denominator, I'll just leave as is, 2 to the 3a times 3 to the b minus 2. All right, now I can focus on the fact that I'm dividing powers with similar bases. And so I have 2 to the power of a divided by 2 to the power of 3a. Well, our exponent law, when you're dividing powers with the same base, I can just subtract my exponents. So this is the same as 2 to the power of a minus 3a. Or a take away 3a is negative 2a. I'm nearly done. Times 3. Again, I got this common base of 3. And again, when I'm dividing powers of the same base, I can just subtract my exponents. So this is going to be 3 to the power of 2b minus 2 minus b minus 2. A lot of subtraction, a lot of negatives going on here. So just got to be a little bit careful. But in the end, what do I have? I have 2 times negative to the power of negative 2a times 3 to the 2b, take away b is just b. And then here's where we got to be careful, but hopefully you see this coming. Minus 2, take away negative 2, same as minus 2 plus 2, which is 0. And so these cancel out. And so I'm done. Those constants cancel out, and so this simplifies to just this. Notice I have an expression that has a negative exponent, but there's no it's not a rational expression. There's no fraction in here. And like I said, hopefully most of this sounds familiar. And going forwards, we just want to become quite proficient and confident working with negative exponents.